Steel, the nation builder, plays the leading role in the development of America by supplying transportation essential to development and use of our great natural resources. Steel, the bone and sinew of our industrial world. Steel, the tool and chief material out of which emerges an endless variety of products essential to modern life and progress. Steel, the homemaker, providing necessities, comforts, and conveniences, giving us a standard of living that's the admiration of the world. Steel, our nation's strong right arm on the land, in the sky, on the water, for the preservation of our nation, our form of government, our American way of life. Whence comes this mighty giant called steel? Steel is the result of man's ingenuity in utilizing one of nature's greatest gifts, iron ore, which primarily is the metal iron firmly combined with the gas oxygen. The first iron used by man was no doubt meteoric iron that had fallen from the sky, such as this specimen. It was used mostly for ornaments. The early Egyptians called it metal from heaven. No one knows definitely how iron was made in prehistoric times, but to see how it might have been done, let's take a look at one of the known primitive methods. A crude furnace was made of clay with the top open. Through the top, the furnace was charged with charcoal. To cause the fire to burn more freely, an air blast was provided by bellows made of flexible animal skins. Elevating the upper part of the bag permitted air to enter through a hole in the top. After it was inflated, pressing down on it forced air into the furnace through hollow wooden tubes. By operating the two bellows alternately, an air blast was maintained. When the furnace had been heated sufficiently, iron ore was scattered over the burning charcoal. Inside the furnace, under the influence of high heat, gases from the glowing charcoal, which is mostly carbon, gradually drew oxygen from the iron ore, leaving metallic iron. After the fire had been forced for several hours, the operator dragged out a lump of spongy metal. This was vigorously hammered to remove slag or cinder and get the iron into compact, usable form. In time, it was discovered that by reheating the hammered iron, it could be worked more easily. But occasionally, the repeated reheating and hammering produced unexpected results. Sometimes the resulting metal, when cold, instead of being soft and malleable, broke into pieces when hammered. During the heating in the charcoal, the iron had absorbed so much carbon that it became hard and brittle when cold. On other rare occasions, the result was a remarkable material, neither soft nor brittle. It had entirely different properties. It was hard and tough, yet malleable. What happened was that during the heating of the iron in the charcoal and subsequent hammering, the iron absorbed the correct amount of carbon from the charcoal and became a form of steel. It should be borne in mind that in this primitive process, the iron was not completely melted, as in the usual modern making of steel. From available information, it appears that the Chinese were the first people to develop a method of completely melting iron in large quantities. The exact method used is not definitely known. Numerous Chinese iron castings, all more than 1,000 years old, have been found, including this iron stove, which was cast at least 1,700 years ago. And here is a hollow image of a huge lion about 20 feet high, cast in 953 A.D. It was not until the 14th century that European iron makers started to melt iron in quantity, by developing a type of furnace shown here in model form. This furnace was erected in 1761 at Hopewell, Pennsylvania, in what is now a National Historic Site administered by the National Park Service. Iron produced was cast into cannon and other war material used by George Washington's Continental troops. The furnace, some 35 feet high, was charged through this open port at the top. The charge consisting of charcoal, iron ore, and limestone was conveyed to the top of the furnace in baskets on carts, such as this. The limestone was used to remove impurities from the iron. A blast of air was forced into the furnace at the bottom through an air duct or tweer. Power for the air blast was supplied by a water wheel operating huge air pumps set above it. Through a hole in the casting arch, the iron was tapped twice a day, and about 25 tons a week was produced. The molten iron was run into molds. Because of a fancied resemblance to a sow and her suckling pigs, this was called pig iron. However, most of the iron used during colonial days was being produced by processes very similar to the primitive method of heating iron ore in a charcoal fire, turning out only about 2 to 6 tons a week. And steel was still being made by reheating the iron in contact with charcoal. Not until 1856 was an inexpensive method developed of converting blast furnace molten iron into steel on a quantity basis by removing the excess carbon. This was accomplished by the development of an air blast converter, of which this is one of the earliest models. This revolutionary development made possible for the first time the production of steel on an inexpensive quantity basis and paved the way for the great steel age. In the modern Bessemer process, the converter is tilted on its side and hot metal from a blast furnace is poured into it through the open top. This converter is then tilted upward and a continuous blast of air is forced through holes in the bottom of the converter up through the molten metal. The oxygen in the air blast combines with the carbon in the molten iron, forming a gas which shoots skyward with blazing brilliance. The Siemens Martin open hearth furnace came into use a few years after the Bessemer converter. This type of furnace now produces 90% of all steel made. The modern manufacture of steel begins with the procurement of raw materials. Most of the #1 basic material, iron ore, is found near the surface of the earth, and open pit mining methods are used. Giant shovels scoop up huge bites of ore. Some of these shovels have a capacity of 15 tons. The trucks are quickly loaded and the ore is on its way. In underground mining, shafts are sunk far into the earth, sometimes as deep as 3,000 feet. At various levels, passageways are driven into the ore body, which is blasted to loosen the ore. After the blasting, mechanical scrapers deposit the ore into chutes, from which it drops into cars. These cars move over a pit and automatically dump into a chute which conveys the ore to a skip, in which it's hoisted to the surface and into railway cars which convey the ore to the loading dock. Arriving at the loading dock, the ore is dumped into pockets for transfer to Great Lakes freighters. The average loading time is about 6 hours. The average load about 10,000 tons. Great limestone deposits that millions of years ago were the bed of an inland sea give up the second basic material used in modern steel making, limestone. The entire wall of the quarry has been shattered by blasting to permit removal of dense, hard material. An electric shovel swings into action. These cars are carrying 600 tons of calcium carbonate, or stone as it's termed in the industry. With the push of a lever, a carload of stone is dumped. Plunging into a huge crusher of cast steel, the complete unit weighs 750,000 pounds. The crushed stone is deposited in huge storage piles, 60 feet high and several hundred feet long. Beneath the storage piles are underground tunnels through which the stone is conveyed to the loading shuttle, which carries 2,500 tons per hour. After hundreds of miles of open water travel, cargoes of iron ore, coal, and limestone arrive at the steel plant and are quickly unloaded. Speed is essential to get the boats away quickly for another load. Train loads of the third basic material, bituminous or soft coal, arrive at the plant where it's converted into coke. This takes the place of the charcoal previously used as fuel. After the coal has been crushed, it's heated in these huge ovens until the moisture and the volatile matter have been driven off. After various byproducts have been extracted from the volatile matter, the gas remaining is used as fuel. After 16 to 24 hours, the red-hot coke is pushed out. It's now 91 to 92% carbon. The first step in making steel takes place in the blast furnace. Here the oxygen and impurities are removed from the ore and the iron reduced to a liquid. Up to the top of the blast furnace go skips with accurately weighed loads of iron ore, coke, limestone, up and down continuously, for one of these giants eats up 3,500 tons of raw materials a day. Making 1 ton of iron requires approximately 2 tons of iron ore, 1 ton of coke, half a ton of limestone, and 4 tons of air. The blast of cold air of the ancient iron maker is now replaced by these huge hot blast stoves and powerful blowers which force huge amounts of preheated air into the furnace. Heating the air increases production and decreases fuel consumption. In striking contrast to primitive methods, modern blast furnaces are scientifically controlled. With the blast furnace in operation, let's see what takes place inside. Up through the mass of coke, iron ore, and limestone is blown a roaring blast of preheated air. At the top, the temperature is about 300 degrees Fahrenheit, increasing at lower levels to a maximum of about 3,300 degrees. As the charge heats, gases formed by the burning coke draw oxygen from the ore as it descends through the furnace, leaving spongy metal similar to that produced by primitive methods. The charge descends through increasing heat until at about 2,000 degrees, the spongy metal absorbs about 3.5% of carbon from the coke. Continuing to descend at about 2,500 degrees, the iron with the absorbed carbon melts. The limestone combines with the earthy matter of the ore, forming slag. The iron and the slag form in molten globules like raindrops, which trickle down through the burning coke. A pool of molten iron is formed on the bottom of the hearth. The slag floats on the iron and is drawn off from time to time. Every 4 or 5 hours, the tapping hole is opened and out rushes a glowing stream of molten iron, termed in the industry hot metal. Sometimes this hot metal is poured into molds and the resulting pig iron shipped to foundries for castings. But usually the fiery river pours through channels which lead it over the tapping floor to huge ladles which hold 125 to 150 tons of hot metal. But before this becomes steel, it must be further refined. So let's take a look at the open hearth department. 90% of all steel today is produced in the open hearth furnaces because of the demand for tailor-made steel in large quantities, which can be produced with this flexible and efficient method. The nearly human charging machine dumps a box of limestone into the furnace and withdraws for another load. The limestone removes impurities from the steel. In similar manner, the furnace is charged with a predetermined amount of scrap metal. As the scrap is already refined steel, it's a helpful ingredient. Lastly, a giant overhead crane brings a huge ladle of hot metal as it comes from the blast furnace. The usual charge is about half scrap steel and half blast furnace iron. An open hearth furnace consists of what might be termed an upstairs and a downstairs. Upstairs is the hearth, in which the steel-making materials are refined. Downstairs are heating chambers containing fire brick, laid in checkerboard pattern. One chamber for heating the fuel, which may be oil, gas, or oil and tar, and another chamber for heating air. The preheated air and fuel move upward, pass into the space above the hearth. Combustion instantly takes place. Currents of flaming fuel sweep over the hot metal, creating temperatures as high as 3,000 degrees. Excess carbon and impurities are burned out. The hot exhaust gases pass down through another set of checker chambers, heating the bricks as they pass between them. Every 15 minutes, the direction of flow of the fuel and air is reversed. In this way, air and gas are heated in one set of chambers, while hot exhaust gases are heating the others. This operation continues for 9 to 12 hours. In the door of the furnace is a peephole through which the melter in charge observes the heat. Let's borrow his colored glasses and peer inside at the boiling, bubbling steel. From time to time, samples are taken for laboratory analysis. To make sure the steel meets the rigid requirements, tests accompany every step in the production of the steel. This is the other side of the open hearth. The heat is completed, and the metal is being tapped, poured into ladles. Higher and higher it mounts until the slag, being lighter than the molten steel, rises to the top like froth and overflows. A giant electric crane, with the greatest of ease, picks up the huge ladle containing some 100 tons, 200,000 pounds of molten steel. The hot metal is poured into molds, a process called teaming. After the hot metal has had time to settle and partly cool and solidify, the mold is stripped off, and we have what's called an ingot. The size and shape depend upon the kind of finished steel to be made. The ingot is placed in a hot furnace called a soaking pit, where it remains until it's of uniform temperature throughout. Here comes our ingot from the soaking pit, a 23,000-pound block of steel starting through a series of operations that will gradually shape it into a form suitable for manufacture into finished steel. As the first step, it is rolled into a rectangular slab. Heavy rolls grip the hot steel and pull it through as a clothes wringer pulls wet clothes. A highly skilled roller from his pulpit, as it's called, handles the operations. After reduction to the desired thickness, a portion of what was the top of the ingot is cut off. This is discarded to assure the elimination of possible defects. Then it's cut into slabs of the desired length. After reheating, the slabs pass through rolls which loosen the scale formed during the reheating. Then they go through 4 sets of rolls termed roughing stands. With each pass, the hot steel gets thinner and longer. It emerges from the last roughing stand in the form of a long strip approximately 3/4 of an inch thick and passes then through another scale breaker and into the finishing stands. Monster machines, marvels of mechanical ingenuity. The total weight of each is well over 1,000,000 pounds. Emerging from the last finishing stand at a speed of about 1,250 feet per minute, the hot rolling process is completed. One of the slabs from our 23,000-pound block of steel has become a strip 600 feet long and approximately 1/16 of an inch thick. The hot rolled strip is coiled or cut into sheets by this flying shear, which works as the strip is still in motion. Hot rolled sheets are made into thousands of products, including truck bodies, buses, freight cars, houses, tanks, pails, lockers, oil drums, and a wide variety of farm implements. After pickling and oiling, it goes through a series of cold reducing mills. Cold rolling produces thinner sheets and gives a more uniform thickness than is possible by hot rolling, as well as a smoother and more highly polished surface. Cold rolled sheets are particularly suited for the production of automobile bodies and accessories, and other products requiring pressing, forming, and stamping, such as kitchen cabinets, refrigerators, stoves, and other domestic appliances. Also office furniture, filing cabinets, and other office equipment. Another cold-rolled steel product is tin plate, from which tin cans are made. After the cold reduction, the strip is washed and dried, then annealed to soften the steel. Then it's put through a temper mill, in which the strip is given the proper temper and shape to produce a flat sheet when sheared. In the standard process of tin coating, the strip is cut into sheets, pickled, and then passed through a bath of molten tin, a controlled coating of which adheres to the surfaces. A recent development in tin plating is the electrolytic method, in which cold rolled strip is tin plated by passing it through an electroplating bath. Here, an electric current deposits a thin coating of tin on both sides of the strip, which is later cut into sheets. During processing, sheets from both methods are carefully inspected for weight and possible imperfections. Feminine eyes are famous for their ability to spot the slightest flaw. Tin plate is used principally in the production of so-called tin cans, which are used for storing and preserving foods of various kinds, as well as chemicals, cosmetics, and innumerable products. Large quantities are used for bottle caps. Tin plate is also used for kitchen utensils, toys, and similar articles. Returning to the hot mill, we see other slabs being made into steel plates. First, they go through a series of roughing stands. The finishing stands complete the reduction, and we have plates from 3/16 to 3/4 inch in thickness. Powerful end shears cut plates of the desired length. Steel plate is indispensable for storage tanks, pipelines, gas holders, boilers, and similar construction. For railway cars, ships, and hundreds of other industrial applications. Next, we see an ingot of different shape and size that is to be made into one of the most widely used products in the industrial world, steel bars. First, the ingot is reduced to what's called a bloom. The bloom passes through a series of roll stands, further reducing the cross-section and increasing the length. It emerges as a hot bar and is cut into what's known in the industry as billets in this flying shear. After being reheated, the billets pass through roughing stands, receive their final reduction in the finishing stands, and emerge as a bar of the desired size, some 325 feet long. After cooling, most bars are cut to desired length. Some, still red hot, are rolled into coils. Bars are used in practically every line of industry. They're forged into crankshafts, axles, bumper bars, springs, bolts and rivets, bars for agricultural implements, reinforcement bars used to strengthen concrete construction in buildings, bridges, and dams, and for an infinite variety of other structural uses. This ingot does not look much like a railway rail, does it? Let's see how modern mechanical ingenuity makes the transformation. In the bloomer, it's passed back and forth between the rolls, then cut into blooms, each of which may produce 2 or 3 rails. After reheating, roughing rolls reduce the cross-section and increase the length. Then back and forth go the rail bars through 3 stands in the mill, growing longer with each pass and smaller in cross-section until they're reduced to the desired size. The last stand puts on the finishing touches and brings the rail to the required size and shape. Hot saws cut the rail to the proper length. The rails are given an artificial curving to compensate for the fact that the head of the rail, being hotter, cools more slowly than the base. To relieve strains and stresses, hot rails are cooled slowly and gradually during the critical period from approximately 900 degrees down to 300. This is done by placing the rails in insulated boxes in which the rate of cooling is controlled for about 15 hours. Over 38 million tons of steel rails are in service today in the nation's transportation systems. Blooms are also used in making a variety of structural shapes, which are formed in rolls specially designed for the purpose, different grooves for different structural shapes. In the finishing stands, the structural shape takes on its final form and emerges as an I-beam. Millions of tons of structural shapes are used in the frameworks of skyscrapers, factories, bridges, ships, railway cars, and other structural purposes. Such is the drama of steel. From the primitive furnaces, turning out a few pounds of crude metal after long hours of labor, to the modern steel mills of our country with the capacity of over 90 million tons of steel yearly, greater than the combined production of the rest of the world. 10 times as much steel is made and used as the total of all other metals combined. It's as vital to modern civilization as air and water are to life. In the home, steel provides countless necessities, ranging from hairpins to kitchen stoves. In transportation, all the way from spikes to streamlined trains. On the farm, from hoes to combines. In construction, from nails to skyscrapers. In industry, steel tools and machinery make practically everything produced, from cigarettes to diesel engines. And for the future, with steel scientists and engineers working as a team, ever striving for new methods, new products, and new uses, it can be confidently predicted that steel will continue to be the backbone of our civilization and our progress.